Swayam Prabha. Digital India. Educated India.
Good morning. We have been discussing fluid flow concepts in the last two classes, where we defined concepts like conductance, that is called flow conductance, similar to electrical analog, which is very useful in predicting the effective pumping speed of a pump at the chamber side, because that is going to dictate the pump down characteristics. And it is very important to understand these concepts of fluid flow, because purchasing a pump or purchasing a chamber or making everything good, but you do not get vacuum, because interconnecting pipe is wrongly designed. So, if the interconnecting pipe is wrongly designed, instead of taking 2 minutes, you will get in 2 days, even though you connect a very good pump. This is what we have been discussing in our earlier lectures, particularly dealing with viscous flow. But the problem becomes more serious in molecular flow, that is dealing with high vacuum conditions, 10 power minus 4, minus 5, 10 power minus 7, ultra high vacuum, where the pumps are very costly and the chamber applications are also very high tech. So, if you make some mistake in making the interconnecting pipes, we are lost totally. You purchase crores of rupees of pumps and then make very high quality shiny vacuum chambers with all metal flanges and gaskets, spending lot of money, and finally you connect it with a long pipe of a small diameter, and you wanted to do some high tech experiments, whether it is a semiconductor device manufacturing or advanced coating or a space simulation or a particle acceleration. Like that, if you want to do, particularly in high vacuum I am talking, with all this cost you are not getting vacuum, and unless you get a very good vacuum you cannot start, particularly like thin film depositions of molecular beam deposition of very slow rate, you need 10 power minus 9 tar. So, monolayer should not be there from the impurities in semiconductor manufacturing. In such circumstances, you must get 10 power minus 9 tar very fast, so that you can do your experiment before the day is over. So, this today's talk we are going to discuss the conductance concepts related to high vacuum and ultra high vacuum applications. Scientifically, we can say we will discuss conductance concepts of interconnecting pipes between high vacuum pumps and high vacuum chambers in molecular flow conditions. So, what are the concepts covered in this lecture? We will be discussing introduction to molecular flow. We will also try to understand how do you start understanding the molecular flow in terms of flux, that means per unit area how many molecules are coming, because just now I told you molecular flow is different from viscous flow. This we have discussed in the last class also. If you want to, you can go through the lecture number 32, because similar concepts are there, but there it is a gas concept, here it is molecular concept. That means, the viscosity concept is out, the continuum concept is out, but still we need to remove a small fraction of molecules only, 99.99% has been removed, but no application has started of high tech nature. So, by removing these molecules, you are not pumping, you are only collecting the molecules and throwing it out to the exhaust of the pump. So, these pumps are called molecular pumps, that is why name came turbomolecular pump, cryo pumps, these are all pumping molecules. Even in diffusion pump, a thick oil molecule is trying to hit a small oxygen or nitrogen molecule. There also the momentum transfer at molecular level. So, we are not catching gas as gas, we are catching as molecules. So, the flow that takes place from the chamber to the pump, that flow is called molecular flow. That is what we will discuss, and in how do you relate it to the actual application of getting a good vacuum to find out the effective pumping speed at the end. That is the final aim, but that requires conductance calculations. So, a good amount of knowledge is required for the engineers, those who deal with high tech applications, to understand the conductance calculations at high vacuum conditions. That we will see from kinetic theory of gases, how do you calculate these conductances in molecular flow. We will also see if complicated shapes are there, like particle accelerators, space simulation chambers, the pipes are not simple circular pipes there can be complex shapes, then engineering is complicated, but still molecules follow some scientific concepts. So, we use Monte Carlo techniques to find out the conductances. Once conductance is obtained, we can use it to get the effective pumping speed. Once we get the effective pumping speed, we can know the time required to get a good vacuum, particularly in high vacuum, and very important when you are dealing with ultra high vacuum. If a small mistake is made, you will not get ultra high vacuum even after a month. Pumps may be very good, chambers may be very good, but if you had made a mistake in conductance calculations and used a wrong pipe, the purpose of getting good vacuum is lost, you can never start your application. So, these concepts are dealt, and we will also have some important conclusions required for process applications. So, coming back to the subject, we all know that Knudsen has given us a beautiful concept, Knudsen number, which is mean free path divided by the diameter, if it is circular pipe, otherwise it is hydraulic diameter. Normally at high vacuum conditions, not in the viscous range, high vacuum conditions means below 10 power minus 3 torr, minus 4 torr, like that, this Knudsen number is quite high, more than 1. That means, lambda is very long, d is small. So, the mean free path, if it is very long, means what? The molecule travels a longer path before it collides with another molecule, but the chamber volumes are fixed. Then what will happen? Molecule will first hit the chamber. After getting multiple collisions with the chamber, at the end of the day, maybe it will come across another molecule by chance, by statistical chance, it will hit. Kinetic theory gives all these things using Maxwell-Boltzmann statistics, all these concepts are very well done in kinetic theory of gases. So, we will have to use that, but we should be having an awareness that molecule collisions are scarce, molecule surface collisions are much more. So, ultra high vacuum, particularly even high vacuum, is dominated by molecule wall collisions. That wall can be a chamber, wall can be a valve, wall can be even pump, wall can be a tube, anywhere. It can be a substrate, varieties of things. So, when we are dealing with flow of molecules, we need to think what is the mean free path between source of gas and the final destination of the gas, whether it is a pumping process or evaporation process, etc. And we have to think that it is not in a continuum flow. Flow is directly dictated by statistical chances. So, if you look at the figure, some molecule may be coming from this side, let us say it is chamber, and here we have a pump. Some molecule can come and get reflected from this side up and again go, finally it will be caught by the pump. But since molecules are independent, the roughness of this surface is of micron level, even submicron level, it is still 1000 angstroms, whereas a molecule is only 5 angstroms. So, at that portion where it is hitting, it depends on the surface profile there. So, we may be thinking that molecule is going from high pressure, relatively high pressure, let us say 5 into minus 5 torr to 5 into minus 7 torr available in the pump side. We may be thinking flow molecule is always going from left to right, but it will not happen. Sometimes chance of it, the molecule coming back is also there. So, molecule can come here and again go back like that. After multiple collisions, it may be coming here. At that time, the molecular concentration in this side is definitely less, because it is in the pump side, molecular concentration definitely more. So, here mean free path will be automatically restricted. So, with some techniques in diffusion pump molecular collisions, turbomolecular pump collisions with the surface, cryo pump adsorption, we can have a pump and pump out those molecules, but first they have to come. Pump has no control of molecules coming towards it. If it comes, I will catch. I can catch fully 70% of the molecules. We can design properly. This high vacuum pump design is a big game we have seen, and later when the system designs for various applications, we will work out all these things. Because lack of time, I just want you to understand this concept. So, the molecule can even go back to the chamber side, or it can go forward in the pump side. It all depends on chance and the relative roughness of this compared to the diameter of the molecule. Okay. In molecular flow, we cannot talk of sucking the molecules. They are only randomly moving everywhere. In that random motion, there is a chance of those molecules coming towards pump. I will be telling another peculiar thing. There may be some molecules from right to left and left to right, but since concentration is much less here, concentration is more, left to right flow will be more compared to this, because from the statistics we can see. That is what I am going to discuss here. The impact rate in our pipe flow, the molecules in an imaginary surface, the impact, that means crossing a particular area, number of molecules on a surface in a pipe flow means within that area, let us say, for unit time, that is called impact rate. That is given by the number density at that point n multiplied by the average velocity divided by 4. This comes from kinetic theory, beautiful derivations are given, you can go through it. Its unit is molecules per centimeter cube, that is the unit of n, and velocity unit is centimeter per second. This velocity comes from the Maxwell-Boltzmann statistics, root 8 k b t by pi m, you all know this. Then from kinetic theory, we also know the pressure is given by the number density multiplied by the Boltzmann constant into temperature. It is not number of moles. If you write number of moles, it will be nRT. If you write number of molecules, it is nkBT. Okay. Now, combining all these three equations, you can get this final equation for the molecular flux per unit area, or we can call it impact rate, which has got a symbol J related to the pressure or the vacuum level and temperature and mass of each molecule and Boltzmann constant. This you can derive by yourself, it is just a rearrangement of the things. So, after understanding this flux molecules and molecular flow and mean free path dominating the whole flow, no viscosity concept. Now, we should have some working formulae to calculate the conductance under these high vacuum conditions. Use that formula to find out the conductance, and with that conductance you try to calculate the effective pumping speed. 1 by S effective is equal to 1 by S manufacturer's pumping speed plus 1 by C the conductance of the pipe that we are using in between pump and the chamber. It is as simple as that. Once we know that, if that effective pumping speed is able to remove the molecules and if there are not much leaks or degassing, we will get very good vacuum, so that we can start our application. So, it is very important to have some equations or some formulae. I tried to give some intermediate steps, but if it is okay if you remember the end equation, because you are not going to do research on molecular theory. Okay. So, these are the formulae we have given for molecular flow in aperture wise or pipe. Aperture means it is a pipe of negligible length. That sort of concept we will get in differential pumping speeds, etc., or at the cryo pump whatever is coming, or even in the deposition time, if an aperture is opened or closed, how much is the flux that is going, that depends on the aperture conductance. So, these conductances of aperture are very important. Later we will see in the thin film depositions or space simulation or even particle accelerators, we will see that. But right now we will say aperture conductance and pipe conductance. Conductance I told you in the first class, it is the throughput divided by the pressure drop. So, if the pipe is reduced to very low dimensions, then we call it as aperture conductance. Otherwise, it is a very long pipe means it is a pipe conductance. A short pipe means an aperture conductance connected in series with the pipe conductance. You have to take weightage of both these things. So, these are the equations for all these three situations. So, aperture conductance, pipe conductance and a short pipe which is nothing but a aperture connected in series with the pipe. So, these are the equations. Where we are starting? Just one slide before we have introduced this molecular flow impact rate. That rate we are taking again here. We are starting here, okay. J, that is the net flux, let us say aperture separating one relatively high pressure, both are in vacuum, relatively high pressure and low pressure, or we can say pump or chamber separated by an aperture. That such situations are there. For example, nanoparticles deposition and all will get such apertures, etc. Even in, for example, your coating applications in cell phone manufacturing, etc., there are some effusion cells where through which you will suddenly get flux of gases. All these things, there will be left to right flux of molecules and right to left molecule. So, net flux is nothing but the J1, which is impact rate per unit area, multiplied by the actual area of the aperture. J2 is the reverse flux multiplied by its own area. So, finally, how many molecules are transferred from this side of the aperture to that side of the aperture? This is J1 minus J2 into A, and using these equations we can convert it into this shape up to here from the kinetic theory. But we also know the definition that throughput is nothing but kBT into dN by dt. Okay. This is also we have discussed earlier in fundamentals. It comes from NKT, etc. From there, throughput is it is a unit by itself, has got a millibar liter per second type of unit. Okay. That throughput is also later we will use another throughput equation, that is conductance into pressure drop, because our main idea is to get conductances. Initially we got molecular theory, the impact rates, that will be converted into dN by dt, net flux, net molecular rate that is going from left to right, that is the pumping action from the chamber left side, right side to the pump. That when you this dN by dt, if you try to substitute here, then you will get throughput. Once you get throughput, you will get a modified throughput equation, because we normally speak about gas constants and molecular weights rather than weight of individual molecule. So, we know the standard equations, capital molecular weight is nothing but individual molecule weight multiplied by the Avogadro number. Similarly, the gas constant is Boltzmann constant into Avogadro number. So, when you do all that, you can get a throughput in this equation. From the conductance concepts in 31 lecture, we have also seen C into P1 minus P2. So, we adding or comparing or simplifying both these equations or rearranging these equations, we will get the conductance aperture, conductance of an aperture formula. Here it is only proportional to area multiplied by this, and of course, it is inversely proportional to the molecular weight square root of inverse, and directly proportional to square root of temperature. Okay. So, for an air, that means you have to use molecular weight of air, effective molecular weight, not nitrogen or this one. If it is a nitrogen, it will be 28, otherwise 32, otherwise 28 point something, 28.4. So, we can at 20 degree centigrade, we have to put everything in Kelvin, we will get this 11.6 times area. This is a very famous formula in vacuum technology. 11.6 times A is the aperture conductance, which also is used in pumping speed calculations of any ultra high vacuum vac. All high vacuum pumps, their pumping speeds are not measured by the working principles. Their pumping speeds are measured by the arrival rates. They are defined by the aperture conductances. If molecules come only, pump can pump. So, the pumping action is dominated by the arrival probability rather than doing something, rather than pumping actions. Later, we have to do research on pumping action. Similarly, for a long pipe, there is another formula, I am not going to derive. For a long length, this is the formula. If you use respect to molecular weight and temperature, you can get the length conductance. This is a long length pipe. Okay. For air, for example, or nitrogen at 20 degree centigrade, if you put, you will get a simple formula, because most of the time we talk about room temperatures, most of the time we talk about air. So, this equation you should keep it always in your fingertips, just like 11.6 A, 12.1 d Q by L. Of course, it will be 12.2 or 12.3 depending on the temperature. For 20 degree centigrade, this one, otherwise you can recalculate. If you are summer, you will have to modify a little bit, you have to take care of that. But what will happen for a short pipe? It is neither an orifice nor a long pipe. So, you have to take a series combination of the entrance combination of that aperture effect, because molecules have to enter into the pipe, there is a probability coming into picture, then it will flow through that. So, flow through pipe is the conductance of a pipe. Coming arrival and then crossing the orifice, that is dictated by the orifice conductance. Both these two conductances can be visualized as a series combination of conductances. Understand? Aperture, pipe. Normally, we neglect the aperture conductance if it is a long pipe, but we cannot neglect if it is a short pipe. If it is a very short, then only aperture. If it is a long pipe, it is only pipe. Most of the time 12.1 d Q by L is good enough. 11.6 A comes in some other applications of ultra high vacuum, where fluxes are measured and particle accelerators, for example. There we use this conductance not for the sake of pump down calculations, even for some flux calculations, which are very important. Even for thin film depositions using molecular beams, when they are coming molecular beam epitaxy units, etc. There also these things come into picture. If on the way from the source of a gas to the substrate, if you keep an aperture, how the things get controlled. This is one way of controlling, precise controlling of various layers, whether it is an optical device like a cell phone, or whether it is a semiconductor device used in laptops, etc. This thickness monitoring, etc. are done with variable apertures, etc. There we will be using this aperture conductance anyway. So, coming to the formula now, in a short pipe we will be using this series combination formula. CL is given by this, CA will be given by this. Okay. By combining all these things and using a simple formula like that, we can get for nitrogen a typical formula 12.1 d Q by L by 1 plus 4 d by 3 L. This is a standard formula used for short pipes. But for those who are using the applications in a simple manner, it is good enough if you remember this formula, or to be precise for various temperatures this formula, because always you may not be using nitrogen gas, you may be using hydrogen, then this cannot be used. So, do not remember this formula just like that. For air, this is a typical thing, mostly you may be using, but you have to use this. For apertures, you have to use this. For air, if it is not air, you have to use this. Other and both the effects, if you want to take for a short pipe, you have to use this. Once you get the conductance accordingly in your application, you get the effective pumping speed. But what happens if it is not a circular pipe? There may be valves, there may be some other combination, big chambers are connected in a particle accelerators, or or even space simulation chambers or semiconductor device manufacturing, varieties of shapes will be there. They cannot be always considered as a circular pipe. In fact, they are not connecting pipes, there may be some flange coupling, after that you are making a connection. So, that flange coupling may be a reducer. So, varieties of complicated shapes may be there instead of a circular pipe. Then what to do? You cannot use these simple formulas. There will be multiple collisions of the molecules arriving, because as it forwards towards pump side, the diameter is reducing. So, you have to use special techniques nowadays called Monte Carlo techniques. You can apply them for different geometries in terms of probabilities, transmission probabilities for the molecules getting transmitted from the chamber to the pump side. And they are not interacting particles, they are interacting only with the chamber. So, different molecules may have different tracks. You have to put millions of tracks, and you have to do it using computational methods, using good old Monte Carlo techniques, and that means you are adding statistical physics and high speed computational capabilities using Monte Carlo techniques. Then also you will get for a particular delta p that we normally encounter. Delta p means P 2 will be pump side and P 1 will be chamber side here, but delta p is not the driving force for the molecules, that was the driving force in viscous flow. So, this also you should remember. In molecular flow, pressure drop is not the driving force, but still there will be net flow from high pressure to low pressure, because at low pressure concentration is less, but molecules come from right to left, but if concentration itself is less, flux will be less. Here concentration is more, so flux will be more. Net will be as if something is flowing, 100 molecules flowing this side, 80 molecules flowing, 20 molecules are flowing. But in viscous flow there is no reverse flow, only whatever is the flow from left to right only. This also you should remember. So, you have to have different steps, you can go through this slide at your leisure, and again the probabilities of molecules hitting back also, that also will be there. You should be extremely careful handling all these situations, and depending on the roughness of the chamber, depending on the roughness of the pipe, you have to change your ideas, and in between there are some complicated steps. So, entire thing is how do you generate a picture of that complicated shape in the computer first, then do the fluid molecular flow dynamics into that, and use statistical things using Monte Carlo. With all these things, it is a big research area, very important area, particularly in high vacuum and ultra high vacuum conditions. I would say ultra high vacuum, which is very important in most modern areas, like all 3-4 areas are there, that is space technology, nuclear technology, and semiconducting technology, and even advanced metallurgical technologies, and various sealed off devices etcetera, of X-ray tubes etcetera. So, varieties of things are coming up in a big way, where these conductance calculations in terms of transmission probabilities and using the aperture conductance from the kinetic theories, you can add all these things. This alpha will be obtained from the programming, and earlier formulas, simple formulas, kinetic theory can be here, and that finally will give you the net conductance, which is a real conductance. If that is used to get the effective pumping speed, then you will get the realistic pump down curves. And these such papers are coming in advanced journals nowadays, like Vacuum Science and Technology and Vacuum and all. We are regularly getting such papers. If you want more details on these things, you can approach me, and we can work out certain projects in colleges or even in industries dealing with high vacuum for high tech applications. We particularly for semiconductor or space or nuclear. If you want, you can approach me, we will try to do something together. It will take its own time, because you have to understand physics, molecular physics, programming, everything. So, that is how if you do that, you will be in a position to calculate the pump down characteristics finally through effective pumping speed, and that will be getting from the effective conductances etcetera, and that will be obtained from the formulae to be used. So, in conclusion, what I want all of you to understand is calculation of conductance in molecular flow is very important. If a small mistake is made, instead of getting high vacuum of 10⁻⁻10 torr, in 1 hour or 2 hours, you may get 100 hours. Just because you made a mistake in interconnecting pipe, or somewhere you are not tightened, there is a leak, or if there is a roughness is more, or if you have bent the things, or unnecessarily you have chosen a long pipe for the comfort. Okay. And you cannot arbitrarily increase the diameter in the urge to improve the conductance. If you increase the volume, that pipe itself becomes a volume. So, you have to optimize all these things, very important. So, a designer, particularly when he is involving high costly pumps like cryo pumps, diffusion pumps and turbomolecular pumps, pumping high tech chambers for particle accelerators and space chambers, semiconductor manufacturing, you must use proper calculations of conductance. Otherwise, you will not get ultimate vacuum, or you will get after 10-15 days, you will not have time to do your main experiments. Particularly if there is a leak or degassing, you are totally in a confused state. You will not be able to do your research or technology at all. So, these conductance calculations, leak rate, degassing, all these things have to be looked into that. So, later we will see what is degassing, what is leak rate, etc. But conductance is fluid flow concept, but it is not fluid, it is a molecular fluid in a molecular flow. Later transition flow, because initially we said viscous flow, now we are saying molecular flow. In between there will be transition flow. So, there will be weightage of that and weightage of this. And we have also seen in viscous flow, the conductance is a function of pressure. Here in molecular flow, there is no pressure at -3 or -4 or -5, it is always constant. That means a constant conductance, because already lambda is much more than d. So, these drag effects are not there. So, P is not coming there. Okay. Conductance in molecular flow is constant, it depends on only molecular weight and temperature. Conductance of viscous flow is depends on the pressure as well as molecular weight and temperature. And molecular flow conductance is always smaller, and in between there will be transmission conductances. And at very high pressures, turbulent and even some venting conditions, we will have choked flow. If you see all these things, it comes under fluid flow, that we will see later. So, today we have understood conductance calculations, which are important to find out the effective pumping speeds in accelerators and high tech applications like where nuclear and space applications and semiconducting applications. So, conductance in molecular flow is over, but we will work out certain worked out examples in the future classes when we deal with applications. Thank you very much.